Hey there, my name is Cade Scallions, and this is my physics project titled Cookie Spread and Heat Transfer, How Baking Surfaces Shape Delicious Physics. Physics is often thought of as something that belongs in labs and textbooks only, but in all actuality, it's everywhere, even in the kitchen. Every time you bake or cook, you're watching heat move, energy transform, and matter changing states. Baking cookies, for example, is a perfect model for studying physics in everyday life. For this experiment, I wanted to look at something simple yet scientifically rich: how different baking surfaces influence cookie spread and texture specifically. I compared three materials, aluminum, steel, and glass, and tested each one at both room temperature and in preheated conditions. By observing the differences in cookie diameter, I measured how efficiently each material transferred heat to the dough. That process reveals real-world applications of physics concepts like conduction, convection, specific heat, and even thermal conductivity. If you think about it, when a lump of cookie dough hits a hot pan, countless physical interactions are happening. Molecules are vibrating faster, energy is flowing from the metal to the butter, fats melting, and water is evaporating. These are the same laws of energy transfer that power engines, design spacecraft, and guide materials in engineering. So throughout this presentation, I'll show how a simple baking experiment can demonstrate five core physics principles while also connecting this experiment to other disciplines like culinary science and materials engineering. By the end, I hope you'll see how something as ordinary as a cookie can reveal the extraordinary physics happening all around us in everyday life. When most people think of baking cookies, they imagine recipes, ingredients, and taste. But what's really happening in the oven is a miniature physics experiment. Every cookie that comes out of the oven is the result of a heat transfer, an energy conversion, and a molecular change. Baking is, at its core, applied thermodynamics in action. In physics, there are three main ways that heat moves: conduction, convection, and radiation. Conduction happens when energy moves directly through molecular contact. When a piece of dough touches a hot pan, atoms in the metal vibrate rapidly and bump into molecules in the dough. This flow of kinetic energy melts the butter, softens the dough structure, and begins a spreading process. Convection comes next. Inside the oven, hot air circulates around the cookies, carrying heat to the upper surface. That airflow keeps the baking environment uniform and helps to brown the tops evenly. And finally, from the oven's heating element, radiation occurs. It transfers energy through infrared waves, and you can feel this same effect when you open the oven door and feel a wave hit your face. That's radiant energy. It's not as dominant as conduction in this context, but it contributes to surface browning and moisture evaporation. These three forms of heat transfer work together to turn dough into cookies, but the real difference lies in how each pan material conducts heat. Aluminum is a fast conductor. It allows heat to flow quickly and evenly across its surface, which causes the butter in the dough to melt faster and the cookie to spread wider. It's also lightweight, so it heats up and cools down pretty quickly. Steel conducts heat a little slower, but holds on to it for a good bit longer. This slower transfer means the cookie has more time to set before spreading completely, creating a thicker center. Glass, on the other hand, has low thermal conductivity, but a high heat capacity. It takes longer to warm up, but once it does, it holds heat very efficiently. That's why cookies on glass pans often bake thicker and continue cooking for a decent little while after being removed from the oven. The differences you'll see between the cookies reflect two key physical properties: thermal conductivity, which is how quickly heat moves through a material, and specific heat, which is how much energy it takes to raise that material's temperature. Together, these values determine how fast energy from the oven transfers into the dough. There's also a related property called thermal effusivity, which measures how efficiently a surface exchanges heat with another object. This explains why an aluminum pan feels colder than glass at room temperature. Aluminum draws heat from your hand faster, even though both are at the same temperature. In baking, that same process means aluminum transfers energy into the dough more rapidly, producing greater spread in less time. When you combine all these principles, you can actually predict how the cookies will behave before they're even baked. Faster heat transfer produces thinner, whiter cookies, while slower heat transfer leads to thicker, softer ones. So even though baking feels like an art, it's really more of a science of heat and energy. The same physical laws that govern engines, electronics, and even planetary motion also shape the cookies cooling on your counter. Now that we've covered the physics behind baking, let's look at how I designed my experiment to test those principles in action. The goal of this project was to determine how different baking surfaces and starting temperatures influence cookie spread. I started by identifying the independent variables, which were the pan material and the pan temperature. I used three common materials: aluminum, steel, and glass, and tested each one under the two temperature conditions, being room temperature and preheated. This gave me 6 total experimental conditions to compare. The dependent variables were the average spread ratio, which tells us something about how efficiently heat transferred into the dough. For this experiment, I used a consistent cookie dough recipe across all trials. Each cookie used precisely 0.7 ounces of dough, measured with a digital kitchen scale to ensure uniformity, even though I bought the pre-cut package. Using the same dough weight was crucial because even small differences in mass or composition could affect how quickly the cookies spread and baked. To maintain controlled conditions, I kept several other variables constant. The oven temperature was set to 350 Fahrenheit for each batch. All cookies were baked on the center oven rack to ensure even heat exposure, which ended up costing me a little bit more time than I would have liked because I could only fit 2 batches in my oven at a time. And finally, all dough samples came from the same chilled batch, so that starting temperature wouldn't affect the results. Before baking, I arranged the 6 conditions into a clear schedule. First, I baked the 3 room temperature pans. Next, I preheated each pan for 5 minutes in the oven before placing new dough samples on top and immediately baking them. This allowed me to isolate the effects of both the material and its initial temperature on the final cookie characteristics. For each trial, I recorded the spread ratio, which compares the cookie's final diameter to its initial dough diameter. To get this measurement, I measured each cookie across 2 perpendicular diameters using a standard ruler, then the average final diameter for each pan by the starting size. I then took a time lapse of each batch of cookies cooling down to see how long it would take for the edges to set and the cookie to fully depress. Each condition was tested with 2 cookies, giving a sample size large enough to calculate reliable averages. After baking, I recorded all data in a table mentioned within my paper. This made it easy to compare how each pan material and condition performed relative to the others. I also made sure to let all cookies cool for 5 minutes before removing them from the pans. That cooling period was very important because residual heat from materials like glass can continue baking the cookie even after it's out of the oven. A clear demonstration of differences in specific heat capacity between materials. Finally, I organized all results into a single table showing the mean spread ratio for each batch. This table made it easier to visualize trends and to compare how preheating or material choice influenced overall performance. In short, this setup allowed me to test a simple, repeatable question. How does the rate of heat transfer, determined by both pan material and temperature, influence the final structure of a baked cookie? By controlling all other variables and isolating these factors, I was able to directly connect the physical properties of the pans to observable changes in the cookies themselves. As previously mentioned, once all 6 trials were completed, I organized the results into a single table showing the average spread ratio for each combination of pan material and starting temperature. The spread ratio compares how much the cookie's diameter increased during baking. It's calculated by dividing the final cookie diameter by the original dough diameter of 1 inch. This made it easy to see how the heat transfer from each pan influenced the cookie's ability to spread. According to the data I summarized, the preheated aluminum pan produced the highest spread ratio overall, averaging a 2.625 inch increase. That means cookies baked on hot aluminum spread almost 3 times wider than their starting size. This makes sense physically because aluminum has the highest thermal conductivity of the 3 materials. It transfers energy rapidly and evenly, so the dough's butter melts almost immediately, reducing its viscosity and allowing the cookie to flow outward before the starches and proteins set. The resulting cookies were wide, thin, and uniformly browned, a clear sign of efficient and consistent heat distribution. At room temperature, however, aluminum spread ratio dropped slightly to 2.4375 inches. Even though aluminum is still a great conductor, starting at room temperature delays the transfer of heat into the dough by several seconds. That small delay means the butter melts more gradually, producing less dramatic spreading. Still though, even at room temperature, aluminum performed better than any other material under the same conditions. Next, steel pans produced moderate spread ratios that fell right between aluminum and glass. At room temp, the average spread ratio was 2.25 inches, while the preheated steel pan reached 2.375. This pattern reflects steel's lower thermal conductivity but higher heat retention compared to aluminum. It takes longer to heat the dough initially, but once hot, it holds that temperature well, creating a steady, uniform bake. The cookies from steel pans were slightly thicker and had more defined edges, a pretty good indication that the dough had a little bit more time to set before full melting occurred. And finally, glass pans yielded the smallest spread ratios overall, confirming that they're the least efficient conductors in this experiment. At room temperature, the average spread ratio was only 2.1 inches, and even after preheating, glass produced just 2.25 inches. These results clearly show that glass transfers heat slowly into the dough. Because it has a low conductivity but a high specific heat, the dough warms up gradually. By the time the butter begins to melt, the outer proteins have already started to solidify, limiting how far the dough can flow. The cookies were noticeably smaller and thicker in appearance, which directly corresponds to slower energy transfer through the pan surface. Across all materials, one consistent trend stood out. Preheating always increased the spread ratio. The difference, however, was most pronounced with metals, especially aluminum, where preheating raised the spread ratio by roughly 0.35 inches, or about a 14% increase in spread. This clearly shows that a hotter surface transfers energy into the dough much more quickly, creating a burst of conduction that melts fats and lowers viscosity almost instantly. In contrast, the preheated glass pan only showed a modest improvement of 0.25 inches, reinforcing that the material's inherent properties limit how fast it can exchange heat, regardless of starting temperature. Overall, these data support the prediction that materials with higher thermal conductivity and effusivity promote greater cookie spread. Aluminum led the group, steel performed moderately, and glass trailed a little bit behind. A perfectly ordered gradient that matches what we'd expect based on their physical properties. This experiment also highlights how even small differences in energy transfer rate can have visible, measurable effects. A 0.5-inch difference in spread ratio between aluminum and glass might not sound that large numerically, but it represents a noticeable difference in cookie diameter and texture. In a practical sense, that's the same principle engineers use when designing cookware, heat sinks, or thermal systems, balancing conductivity and retention to optimize energy flow. So the numbers in the table don't just describe baking performance, they're a direct reflection of the physics at work. Each spread ratio quantifies how effectively heat moves through a material and into a soft, semi-fluid system. It's a simple experiment, but the results demonstrate real thermodynamic relationships you can literally see on a cookie sheet. All in all, the results of this experiment clearly demonstrate how heat transfer efficiency influences cookie spread, and by extension, how physical properties of materials directly shape real-world outcomes. While the project may seem simple, it represents the same thermodynamic principles that apply to industrial design, manufacturing, and even energy conservation. Across all 6 conditions, aluminum consistently produced the greatest spread, especially when preheated. This outcome confirms the hypothesis that materials with high thermal conductivity and low specific heat will deliver energy into the dough more rapidly. The faster the dough reaches its melting threshold, the sooner butter liquefies and the dough's internal viscosity drops, allowing it to flow outward before proteins and starches solidify. The physics here is rooted in Fourier's law of conduction, which states that the rate of heat transfer through a material is proportional to its thermal conductivity and the temperature gradient across it. Since aluminum's conductivity is far higher than glass, it transfers energy almost instantaneously, producing that broad, thin cookie shape. By contrast, glass is a poor conductor, but it also has a high specific heat capacity. It takes longer to heat up, but once it does, it retains that heat. This means that dough warms more slowly and unevenly, delaying the phase change of fats and limiting spread. The glass pan essentially acts as a thermal buffer, absorbing energy rather than immediately releasing it into the dough. Even when preheated, its inherent resistance to heat flow limits how much additional spreading occurs. Steel, which sits between aluminum and glass in both conductivity and heat capacity, produced intermediate results. This demonstrates an important balance: slower than aluminum, but more stable in maintaining temperature. In engineering contexts, steel's behavior mirrors what's often seen in mechanical systems. It provides consistent, predictable energy transfer, even if not the fastest. These material differences directly reflect how the microscopic structure of each pan influences the macroscopic results. Metals conduct heat through free electrons, which move easily and rapidly transmit energy. Glass lacks those free electrons. Its structure is amorphous and rigid, so energy passes only through lattice vibrations, which are far less efficient. The experiment's numerical results, where aluminum spread ratios average 2.8 and glass just 2.1, make that physics visible and measurable. From a thermodynamic perspective, this experiment also highlights thermal effusivity, which measures how well a material exchanges heat with its surroundings. A high effusivity material like aluminum draws energy into contact systems quickly, whether that's a cookie dough ball, a heat sink, or a solder joint. This property explains why aluminum feels cold at room temperature and why it instantly melts butter on contact. It also explains why glass pans coast after baking. Their high specific heat releases stored energy slowly, continuing to cook the food even after removal from the oven. Beyond physics, these results have valuable interdisciplinary implications. In culinary science, understanding these thermal properties helps chefs and food scientists control texture, moisture, and flavor development. A cookie's structure, whether soft and thick or crisp and thin, depends directly on how heat moves through the dough. Professional kitchens often use select aluminum pans specifically because of their high conductivity and how it ensures consistency, while glass pans are used for dishes where slow, even heating is preferred, such as casseroles or custards. In materials engineering, these same laws determine the choice of metals in everything from cookware to computer components. Designers must balance conductivity, durability, and cost. Aluminum's behavior in this experiment mirrors its performance in real-world applications. Quick to heat and cool, lightweight, and efficient. Meanwhile, steel's steadier performance reflects why it's used in structural and load-bearing systems that require thermal stability. There's also a sustainability connection here. Understanding material efficiency can reduce energy consumption. A pan that transfers heat efficiently requires less oven time to achieve the same result, saving electricity or gas. Small-scale household experiments like this can actually mirror industrial energy studies, helping us think critically about how everyday materials influence energy use and performance. In conclusion, this project illustrates that physics is not limited to equations or laboratory setups. It's alive in everyday activities. A simple baking experiment revealed how thermal conductivity, specific heat, and effusivity govern outcomes we can both see and taste. The data shows a direct and predictable relationship between material properties and cookie spread, confirming the foundational principles of heat transfer. By connecting physics to culinary science and materials engineering, this experiment demonstrates how interdisciplinary thinking deepens our understanding of both science and daily life. It reminds us that every time we cook, build, or clean, or even design, we're really just applying the same universal laws of energy and motion. And sometimes those laws taste as good as a freshly baked cookie.